Sass Class with Amanda. Hey! In this video, we'll be picturing distributions with graphs. Our learning objectives are to determine what a quantitative variable is and to represent a quantitative variable graphically. It's not listed as a learning objective, but we will be comparing what we do in this video to what we learned about categorical variables in another video. Alright, so to start, let's just consider this simple data set, 4 individuals. Each individual is a food, broccoli, carrots, yogurt, a red apple, and what is listed here are the number of calories in a broccoli, okay, the number of calories in a serving, so this is all serving size, and a serving size of carrots, and 100 in a serving size of yogurt, and 72 in a serving size of some red apple. Okay, so the individuals, and I already said this, but we'll just write it down here. Who are the individuals? And we said those are the foods. Okay, and what we want to talk about, again, just like when we were talking about categorical variables, is what does the number represent? Okay, and we see that the number here represents the number of calories in a given individual. And remember that for categorical variables, the number represented the count or the number of individuals that fell into a certain label. And here we have a number with a unit of measurement. Okay, so this is key for quantitative variables. A number with a unit of measurement. So we'll underline that because that's key. All right, so we talked about this data a little bit and we understand what we're seeing, which is great. So now we'll talk about how we can visualize quantitative variables. And remember, our quantitative variable for this data set is the number of calories in a food. Okay, so the first way we'll learn about is a stem plot. And the way a stem plot works is we separate each data point into a stem and leaf part. Okay, and so as I define each of these things, you can think of, here's a horizontal line, here's a vertical line, and one part is the stem and one part is the leaf. Okay, so hopefully that helps you understand how to think about the visualization. Alright, so our stem can be defined as all digits except the last. Okay, and since this is a nice partition, our leaf will then be the last digit in a number. Alright, so for our data set, we want to think about what will this look like. And let me just remind you, we have the numbers 50, 25, 100, and 72. So if the stem is all digits except for the last, and the leaf is the last, then 25 will be 5. So for the stem and leaf plot, we want to put it in ascending order. Okay, so the smallest number goes first, and then the largest number will go last. So the smallest number in our data set is a 25, so we put 5 here because it's the last digit, and we put a 2 here because it's all digits except the last in the number 25. And we'll do the same thing for 50, 72, and now 100. Okay, and notice that in my leaf I'm putting the ones digit, okay? And in my stem, I'm putting the tens digit. Okay, I know this is going all the way back to elementary school when we talked about the meaning of digits, or maybe it was more recent. It depends on your educational background. But so tens is always going to be, you know, the 20, the 30, the 50. When we get to 3 digits, then it's 10, 11, 12, etc. I have to apologize, there's not enough room in the skeletal notes for the rest of this portion of the discussion. What we want to do when we're dealing with a graph of a quantitative variable is to describe the graph. And the 3 things we want to describe is shape, midpoint, also known as center, spread, and any deviations. Okay, so for a stem plot, what we have to do is we have to turn our heads. And so I'm going to draw a head here so that you can put yours in the same position, and we're looking through the head from the back, okay? So here's your eye, here's another eye, and then here's your sight, okay? And then here's your nose. Okay. So you're looking at it so that the leaf is the top layer and the stem is the bottom layer. So I guess another way to think about this is like this, where we have 2, 5, 7, and 10, and then 5, 0, 2, 0. Okay, so when we look at this, we see that this has no shape whatsoever. It's very flat or uniform. Okay, so here we can say we have a flat or uniform shape. Right? So midpoint or center, when we're not specifying center, which we'll learn in another video that there are 2 types. Generally you talk about the midpoint, and the midpoint you can also think of as the median. So we have 4 data points here. Where's the center of these data points? It's between 50 and 72. And so what do we say for our midpoint? Well, we say it's between 50 and 72. And then our spread is always the min to the max. So we just have to figure out what the minimum value is, which is 25, and what our maximum value is, which is 100, and that's our spread. And any deviations. Well, a deviation would be if there's some sort of gap, okay? So in this representation of the data, there isn't like an obvious deviation, okay? And without more numerical analysis, we can't really say what a deviation might be. So here we would say no, or none, or NA. Alright, so still continuing with this example and talking about graphical representations, well, the important thing to know here is that graphical representations are only as interesting as the statistician makes them. Okay? We chose to represent the values here as they are, as 25, 50, 72, 100, but we can very much change those representations for the values. For example, we can round, okay, and what can we round them to? Well, 25 can be rounded to 30. And 50 is going to stay the same, 72 can round to 70, so we're rounding to the nearest 10, okay, and 100 will stay the same. So what does this do for our stem and leaf plot? So our stem and leaf, Well, we don't want to represent our data the same way we did before. Okay, so we don't want this to be the tens place and we don't want this to be the ones place. The reason why I round to the nearest tens is so that we can take our leaf and let that represent the tens position, and our stem can represent the hundreds. Okay, and so how does this change? Well, 30, 50, and 70 are going to have a 0 here, and 100 will have a 1. And then what we have is 30, 50, 70. So each of these numbers represents a different data point, okay? In your textbooks or literature in general, you'll see that these numbers are much closer together than I'm putting them. There will never be a comma, so don't use commas. We want to do common practice. But when I'm writing this out by hand, I will put a small gap between the numbers so that it's easier for you guys to understand, okay? And I will assume when you're creating your own stem plots by hand, you'll do the same thing. But when we start learning how to do this in R, these numbers will be very close together, and it's up to you to remember that each of these digits represents a different data point. Okay, and then 100 will have a 0 here. Okay, now you should notice that the shape, our shape here, is much more interesting, right? So what this shows us is the data is right skewed. Okay, that is a term that we're learning for the first time. So right skewed. And the reason why it's right skewed is notice that this tail is pointing to the right, okay? If it helps, you can imagine this being, you know, Barney the dinosaur. Okay, and his tail is pointing to the right. And if it was left skewed, then Barney's tail would be pointing to the left. Okay, it's a very easy way to remember what is right skewed and what is left skewed. Students get confused all the time, so please draw the dinosaur if it helps. Alright, so this shape is more interesting and it gives us more information about the data, right? So just looking at the original data, we know that 25, 50, and 72 are different than 100 in many ways, okay? But this shape right here just says that they're all very, you know, they're all on the same level of interesting. But this stem plot here tells us that, you know, 30, 50, 70, they're all less than 100. They should all be grouped together. And 100 here is sort of on its own. Okay? But they're not far enough apart that there is a deviation from the pattern in any way. Okay, so whoever ate this meal of vegetables and fruits is a very healthy person. That's what this stem plot tells me.
My name is Llama, and I'm here to teach you stats, skilling you up with them cold hard facts. We live in a world of technology. They're collecting information on your humanity. Social networks, gaming, and in-home software. Statistics helps us be more aware. Haters gonna hate my spicy lyrics. Why you gotta be so mean? Pulling me towards your extreme moods, but the median never fails to center me. 50 to my left, 50 to my right. Got these correlation and regression tools, forget them fools. My name is Llama, and I'm here to teach you stats, skilling you up with them cold hard facts. My name is Llama, and I'm here to teach you stats, skilling you up with them cold hard facts. The mean of the means is the mean. The mean of the means is the mean. The mean of the means is the mean is the mean of the means is the mean is the mean. Be careful not to fall in love. Statistical seduction from above. Your shape so beautifully symmetric to the eye with a single peak so high. I hypothesize and can testify that your p-value is the smallest I've seen. Mix that with a large power and I reach ecstasy. Your residuals defy the rest. A small scale randomized pattern tells me you are the best. Hey. My name is Llama, and I'm here to teach you stats, skilling you up with the cold hard facts. My confidence is so high, 95%. My margin of error so narrow, 1/10. Can you feel me? Can you feel me? I estimate your population parameter based on only one sampling. Oh, haven't the frequentists told you about me? We live in a world of data, attempting to understand life by statistical strife. The implicit bias of cops, success rate of them jocks, medical advances, and AI romances. Statistics.